So, we were talking about exact sequences. A sequence of modules and homomorphisms so on is said to be A modules and A homomorphisms is said to be exact if kernel phi I minus 1 is image phi I for all I. Okay. We saw some examples. Let us look at some of the nice properties. So, suppose I have an exact sequence. So, let n be an A module, let 0 to m prime. So, did I define what is a short exact sequence? No. Okay. An exact sequence of the form zero to m prime to m double prime to 0 is called a short exact sequence. So, this is exactly what we saw last time, examples. In fact, the examples were of short exact sequences. So, if you have a short exact sequence, this map will be injective, this map will be surjective, and kernel of this map is equal to image of this map. That is precisely what is a short exact sequence. Okay. So, let m prime to m to m double prime be an exact sequence of A modules. Then I have home m double prime n to home m n to home m prime n. I have this, given this I have this exact sequence, I mean I have this sequence, right. So, what we have is this is an exact sequence. So, what this property is referred to as home functor is left exact. See here, even if I have a short exact sequence, when you apply home there, you need not necessarily have like this, okay. But I am looking at exact sequence of the form m prime to m double prime to 0. Yeah, we have the other one as well. We have that I will come to the next corresponding. If I have 0 to n prime to n double prime, then home m n double prime to, that's again exact. So the exactness, even if I have this, I won't necessarily have this exactness. Even if I have a short exact sequence, this need not be a short exact sequence, but I have exactness at the left side. When you apply home, this injectivity is always there. So that is what is known as left exactness of home functor. Home functor is left exact. Okay. So let us try to prove this.
There, if that is right exact given.
Yeah.
Then you can prove that this is left exact.
This is, if this is exact, then this is exact. What more are you saying?
Means I am saying that maybe in this proof record the injectiveness of the above map.
Injectivity is there. This one.
Means suppose m prime to m there is some map f,
Huh.
and so it induces the map from there f star.
No, one can, there are examples where this, even when this is injective, this map is not surjective.
Yeah, that is okay.
Okay, let us go through the proof. So see here, okay, let us call this map f and g. So therefore this will be g bar, this is f bar, right. G bar, so we want to say that g bar is injective and kernel of f bar is same as, to show that one, g bar is injective and kernel of f bar is same as image of g bar. Okay. So how do we do that? Let us try to prove the first one. Suppose g bar takes a homomorphism to 0. So let h be in home m double prime n such that g bar of h is 0. But what is g bar of h? H is from m double prime to n. G bar of h is a homomorphism from m to n obtained by composing with g. G bar of h is 0. That implies that h of h composite g is 0. Okay. We want to say that h is 0, right. That means if I take any element of m prime, h of that element is 0. But now if I take any element of, so h composite g of m is 0, this implies h of g m, so this I should write 0. But what is g m? G of m, m double prime, this is the g is surjective, therefore g of m is m double prime. This implies that h of m double prime is 0. Given that this map, this is exact. Okay. So this says that h is 0. That says that g is G bar is injective. Now we want to show that the second part, kernel of f prime f bar is contained is equal to image of G bar. See, whenever we are talking about this exactness, here one thing can be, I mean, when you have to prove these two are equal, we have to say that this is contained here and this is contained here. Most of the time one of the inclusions follow very quickly. See here, if you look at this, kernel of G is contained in image of f, right, or in other words G composite f is 0, image of f is equal to kernel of G. So, if I take an element, I take from here, go here and then further go to m double prime, it is going to be 0 because this image is contained in the kernel. So, this is always 0. Now, what happens in this case, what is our f bar composite G bar of a homomorphism? Let us take H. What would this be? This would be H composite G composite F, right. That is precisely f composite f bar composite G bar of H, but G composite F is 0. So, therefore, this is 0, which implies that image of G bar is contained in kernel f bar. Now, we want to show that image of G bar contains kernel f bar. So, let us start with an element in kernel of f bar. Let H be in kernel of f bar. So, what is an element, what is this map? H is a homomorphism from m to n. So, I have m to n, this is H, I have these maps m double prime and m prime, this is f, this is G. What is that I want to prove? I want to show that there exists some H prime in hom m double prime n such that G bar of H prime is H. But what is G bar of H prime? This is H composite G is equal to H prime composite G is equal to H. So, I am looking for a map from here to here such that this diagram commutes, or in other words H is precisely this, right. This is what we are trying to prove. So, now there is a way out. We want to define a map and say that this is precisely, we want to define H prime and say that this is precisely the map that works. So, I start with an element here and I want to get an element here. What is that one does? You start with an element, we have to make use of the fact that the given sequence is exact. This is surjective. If I take an element, I have a pre-image here, okay. And what we want is, if you look at that pre-image, you go there and come here, that should be same as that element going here directly through H. So, I just define H prime, I take an element here, its image should be H of the pre-image. But here there is a danger, there could be many pre-images. So, which one? Okay. So, first let us try to define this. Let x be in x double prime be in m double prime. That implies there exists x in m such that g of x is equal to x double prime. Define h prime of x double prime to be equal to h of x. With this definition, at the moment this is not well defined, because there could be many x that satisfy this property. Okay. So, let us take, let us say so this is, first we need to show that h prime is well defined. How do I show that well definedness here? If I show that whichever pre-image I choose, it does not matter. Okay. They will be mapped to the, if I choose two pre-images x1 and x2, if I show that h of x1 is equal to h of x2, we are done. Okay. So, let us do that. Let x1 x2 be in M with g of x1 equal to g of x2 equal to x double prime. G of x1 minus x2 is 0. This implies g of x1 minus x2 is 0, or in other words x1 minus x2 belongs to kernel G, but we know that sequence is exact. Therefore, kernel G is equal to, or in other words there exists some x prime in M prime such that x1 minus x2 is equal to f of x prime. It is in the image of f, or in other words there exists some element in M prime which maps to x1 minus x2. So, this implies that x1 is equal to x2 plus f of x prime. Now, therefore, what is h of x1? This will be h of x2 plus h of f of x prime. Now, we have not used the fact that h belongs to kernel of f prime. H belongs to kernel of f prime. This means that f bar of h is 0, or in other words h composite f is 0. And what is this now? This is h composite f of x prime, which has to be 0. Since h composite f is 0, h of f of x prime is 0, and that implies that h of x1 is equal to h of x2, and that implies that h prime is well defined. One needs to prove that this is an A module homomorphism. So, by definition h prime, by definition G h prime composite G is equal to h. By definition this property is true. right. If I take any element here, go here, then this is by definition we have defined it that way. So, therefore, or by construction whatever you say, H prime composite G is H, or in other words G bar of H prime is H. But still we need to show that H prime is an A module homomorphism. But that's again straightforward. How did we define H prime? Suppose I take x1 some x1 plus x2 here, x1 and x2 here, we want to say that H prime of x1 plus x2 is same as H prime of x1 plus H prime of x2. But if I take x1 plus x2 here, for x1 I have a y1 here, x2 I have y2 here, therefore y1 plus y2 goes to x1 plus x2, therefore H prime of x1 plus x2 is same as H of y1 plus y2, but H of y1 plus y2 is same as H of y1 plus H of y2, but that is same as H prime of x1 plus H prime of x2. Similarly, you can check the scalar multiplication property as well. So, therefore, this is easy to verify. So, therefore, H prime belongs to home A M double prime n. So, this implies that the home sequence is exact. Is this clear? So, this is what we have done here is kind of diagram chasing. We have to define a map from here to here. From here we went to this one, and then we looked at, we know there exists, we defined this map here. A similar, see, given we looked at this exact sequence m prime to m double prime to 0, and applying home dash comma n. Instead, if you have similar proposition, I will leave this for you to write down a proof. Let 0 to n prime to n double prime be an exact sequence. Then 0 to home m n prime to home m n to home m n double prime is exact. So, if I call this f and g, this is f bar and g bar. This map takes, so if I have h here, f bar of h is f composite h composite f, okay, and similarly g prime. So, in this case again one can prove that f bar is injective and kernel is equal to the image. So, here also you have to construct, given an element in the kernel, you have to construct an element in the image. Same way diagram chasing, I will leave it to you to do that, okay, and you should do that, because just listening to me what I have done and copying down from the board, that does not give you feeling for it. So, you write down this proof completely. You have a prototype, okay. Just follow the prototype and then write it down. We will do one more property which has a even better diagram chasing, that is even more fun. So, this I will leave it for you to complete. Let 0 to m prime to m double prime to 0, n prime to n double prime to 0. So, I have these maps u1 v1 u2 v2 f prime f double prime. So, when you have a diagram of module homomorphism like this, we say this is a commutative diagram if at any point from here, let us say for any element here, you can reach here by two ways. One is first come here and then come here, or another way is coming here and coming here, both are same. This is said to be commutative if f composite u1 is same as u2 composite f prime, and v1 sorry f double prime composite v1 is same as v2 composite f. Okay. So, let this be a commutative diagram of A modules and homomorphisms. Then we have an exact sequence involving kernel and then the sequence 0 to kernel f prime to kernel f to kernel f double prime to co-kernel f prime to co-kernel f to co-kernel f double prime to 0. So, I will call this map u1 bar, this is v1 bar, this is u2 bar and this is v2 bar, and this is exact where the map D is defined as follows. Do you understand the sequence? If I have a commutative diagram like this, then from kernel, kernel f prime is a map, a submodule of m prime. This kernel f is a submodule of m and kernel f double prime is a submodule of m double prime. So, first what it says is that you restrict u1 to kernel of f prime, it will be mapped to kernel of f, u1 of kernel of f prime will be contained in kernel of f, that is easy to check. okay. And similarly here, and on the other side this is u2 bar and v2 bar are the induced maps. So, what is co-kernel of f prime? It is a quotient module of n prime. Co-kernel of f is a quotient module of n. What this says is that there exists a map u bar is the map induced by this homomorphism u2 bar. So, u2 bar of some element x prime is u2 x bar, okay. And that will be well defined, and you know it will be homomorphism from here to here, a module homomorphism, and similarly v2 bar. So, these are to start with the existence of those maps. Now, what it says is that u1 bar is injective, which is pretty much obvious because u1 is injective. If I have that map u1 bar which maps from kernel f prime to kernel f, once I show that u1 bar maps from here to here, this injectivity of this is pretty obvious because of the injectivity of u1. Next thing you need to show is that there is a map from v1 bar from here to here, okay. Here it is exact, that is what we need to prove. I will come back to that. So, I will just first I will show that this kernel, I mean u1 bar of kernel f prime goes inside kernel of f, okay. Okay, I will come to the definition of, maybe I will do the definition of D first. So, I want to define a map from kernel of f double prime to the co-kernel of f prime. So, I want to define a map from a submodule of this to a quotient module of n prime. So, what do I do? This is, yeah, we have to keep chasing the diagram. I start with an element in the kernel of f double prime. So, let x double prime be in kernel of f double prime. I want to define, I mean I am trying to define what is D from here to here, okay. So, I start with an element in the kernel of f double prime. Now, this is a submodule of m double prime, therefore, there exists some x in m, there exists x in m such that v1 of x is equal to x double prime. Surjectivity of v1. The first row, okay, I did not say this, commutative diagram of A module homomorphisms with the rows being exact. Okay. The first and second rows are exact. Okay. So, therefore, u1 that v1 is surjective, and hence given this x double prime I have an element in x in m such that v1 of x is x double prime. Now, what can you say about v1 of f of x, sorry, f double prime of v1 of x? v1 of x is x double prime and x double prime is in the kernel of f prime, therefore, this is 0, and that implies diagram is commutative. So, you go to m double prime and come to n prime, or travel the other way, you are going to get the same element, or in other words we have V2 of f of x is 0. That means f of x belongs to kernel V2. But what is kernel V2? This is image V1. Therefore, there exists some z prime in n prime such that V1 of Z1 is sorry this is image of U2. So, U2 of Z1 is f of x. Okay. So, what have we obtained? We have started with an element x double prime here, okay. We got a pre-image here and said that image of that under f is in the kernel of V2, therefore, I have an image in n prime, and we are indeed trying to define a map from kernel of this to a quotient of this. So, we have now got hold of an element in. So, immediately what we should do is define d of m x double prime to be the image of, I mean see, we want to define to a quotient of n prime. So, define it to be z1 bar, z prime bar, whatever. Okay. This is, yeah. Now, we have to tackle the first thing that we need to check is this is well defined or not. I mean, we have travelled a lot, okay, from x double prime to reach z1 prime. How do we know whether we travel a different path, we arrive at a different element? Okay. So, define d of x double prime, d from kernel f double prime to co-kernel of f prime by d of x double prime equal to okay. So, first to show that d is well defined, so here how do we show that this is well defined? I mean, where are the issues? To start with, I am taking an element here and going back here. Here there could be many pre-images. Okay. So, first if I choose two elements here, two different elements here, whether that would make a difference or not. Once we see here, once we reach this stage, there exists, when we say there exists z prime in n prime such that this is true, this z prime is unique because U2 is injective, the bottom row is exact, that means U2 is injective. So, if I know that there exists an image that is unique, there is no confusion here. So, we only need to deal with if I choose two different elements that go to x double prime, that would not create any trouble. So, let us try that. Let x1 x2 be in M such that V1 of x1 equal to V1 of x2 equal to x double prime. Once we reach here, what is the next step? Once you see this equation, what should come to your mind next? V1 of x1 minus x2 is 0. That means x1 minus x2 is in kernel of V1. But we know what is kernel of V1. What is kernel of V1? This is image of U1. What does that say? That says there exists some y prime in M prime such that x1 minus x2 is equal to U1 of y prime. Or in other words, x1 is equal to x2 plus U1 of y prime. Okay. Now let us see, once I prove that, see, we need to prove that pre-image of fx1 fx1 minus fx2, that is 0 in the co-kernel. What we need to show is that f of x1 minus x2 is 0 in the co-kernel. That is, our map is defined from here to here, not into n. In n it need not be 0, but in the co-kernel if that is 0, then the corresponding pre-images will give you 0. I mean the difference between the corresponding pre-images. So f of x1 x1 is x2 plus something. Now let us look at what is f of x1 is equal to f of x2 plus f of u1 of y prime, right. Now see, if I take f of x is anyway in the kernel of V2, because f of x1 and f of x2 both are in the kernel of, and this is also in the kernel. See, what is f of x1? What is f of x1? Sorry, I mean what we want to show is, I am saying how did we arrive at this? See, f of x1 is the pre-image of x double prime. Okay. x1 is here, f of x1 is here. Now you go, I mean V2 of f x1 is same as f double prime of x double prime, but that is 0. See, x1 is here, this is the pre-image of x double prime. X double prime is mapped to 0 here. Therefore, this fx1, this is mapped to 0 under V2. So therefore, f of x1 similarly f of x2, both of them are 0. That is how we have chosen. Where is x double prime? What is x double prime? We are defining a map from, right. We have started with an element in kernel of f double prime. So therefore, this is fx1 is 0, I mean V2 of fx1 is 0, V2 of this is 0, therefore V2 of this is 0. Okay. So if I show that, you know, modulo the co-kernel, these two are same, I mean modulo the image of f, these two are same, we are through. But is this not what we have shown now? F of, if you now take, okay, so let us, so this now fx1 there exists z1 such that what was that, u2 of Z1 is equal to x1, oh sorry, f of x1, yeah, f of x1, and there exists u2 such that z1, there exists z2 such that u2 of z2 is f of x2 plus f of u1 of y prime, because this is also in the kernel of u2, which is in the image kernel of v2, which is in the image of u2. Now what is, see, u2 of z1, this is not what I want to say, yeah sorry. So this is f of x1 minus x2 is f of u1 of y prime, but f of u1 is u1 of y prime is same as, see, f of u1 of y prime is same as u2 of f prime, u2 of f prime of y prime. Now if I apply, so for x2 I have a z1, for x1 there exists z1 in n1 n prime, and for x2 there exists z2 in n prime. What would be u2 of z1 z1 minus z2? This is equal to f of x1 minus x2, which is equal to u2 of f prime of y. But now u2 is injective, so that implies that z1 minus z2 is equal to f prime f prime of y prime, there is a y prime, that says z1 is same as z2 plus f prime of y prime. But what is co-kernel of f prime? Co-kernel of f prime is, this is n prime modulo image of f prime. So modulo image of f prime, z1 bar is same as z2 bar. So this implies z1 bar equal to z2 bar in n prime mod image of f prime, which is co-kernel of f prime. So what we have shown here is that the map D is well defined. So in the next class I will probably take one or two of them and show that they are, this indeed maps from well defined map from here to here, okay, and I will leave the rest of those easy checkings to you to complete it.